Hello, everyone. So I'm Devina Misra. I'm a postdoctoral researcher working with Manuel Binaries at NTNU in Norway. And today I will be talking to you all about some recent work that we have been doing, studying the formation of cannibalistic millisecond pulsar binaries using detailed stellar evolution. So considering that this is literally the last talk of this workshop, I'm not going to go too much in detail into the introduction, but just mention some relevant numbers that basically to keep in mind while I present my results. So, for instance, these systems are also known as spiders, very compact orbital periods, so less than 1 day, more or less. Mainly two groups, so you have black widows and red bats based on the masses of their companions. And the two general processes, or the two general phases that I will focus on is firstly is the accretion phase, which is where the actual spin-up happens, and the radio pulsar phase. So firstly, for the accretion phase, the mass, as mass is transferred onto the neutron star, it spins it up, and basically that is used to calculate the spin of your resulting millisecond pulsar, if it is one. However, I am using this criteria to limit the accretion, so to sort of introduce a non-conservative nature to the mass transfer phase, and this limit basically defines the lower limit below which thermal viscous instabilities would basically destroy your accretion disk. Then we move on to the radio pulsar phase. So once you have your highly spinning neutron star and you no longer have a Roche loop overflow mass transfer phase going on, as it spins down, it emits this energetic wind that basically ablates the companion, which is where the cannibalistic nature comes from. And the spin down is basically defined using this equation that is for a spinning dipole. Okay, so now to define this pulsar wind irradiation phase, I am using the description as done by Stevens et al. In 1992, where they basically use the spin down luminosity calculated using the spin and the rate of change of spin. In this equation that calculates the mass loss that is generated from the companion surface. There is an efficiency factor here because we don't really know how efficient this process is. And we will investigate further, as you will see, what values of this efficiency factor might help in our spider binaries. Okay, so the code that I'm using is Misra, which is a stellar and binary evolution code. I look at a range of neutron star masses, a range of companion masses going from low to somewhat intermediate masses in the companion, a range of orbital periods, so 0.6 to 4 days. I look at 3 different values of beta, which is basically the fraction of mass that is not accreted by the neutron star during the mass transfer phase. And then I look at 4 different values of the F pulsar, which is this efficiency during the radio pulsar irradiation process. So going from no irradiation to quite high irradiation at 0.5. Also, I will point out that, generally, theoretically and observationally, quite non-conservative values of beta are supported, and we will see how that compares to the spider binaries that we have simulated. So firstly, I will look at the final pulsar spins in our simulated grids for 2 values of beta. So we have beta 0.3 and 0.7. And I'm comparing this to the observed spins of black widows, galactic black widows. And I'm separating the two I'm separating the binaries into 2 groups. So you have ones where the final neutron star mass exceeded the value of 2.5, which is the upper neutron star mass limit that we chose. Just because then otherwise I was getting sub-millisecond pulsars, which have not really been seen. Okay, so then if I just look at the minimum spin in both the cases, firstly, also, like, since this is not a population synthesis study, I'm just running a grid, so I cannot really compare the shape of this distribution to the observations. The main point is to see if we can reproduce any of the observed spins. Okay, and if we look at the minimum spins and the corresponding final mass and compare it to this pulsar, which is the fastest spinning pulsar that we know of so far, J0952, with a spin of 1.4 and final mass of 2.3. So it seems to match pretty well with the case of a more conservative beta. The thing is that because of our assumption of an X-ray irradiated accretion disk, it is already implicitly introducing non-conservative behavior, and then the additional beta accounts for anything that may not have been taken into account. For example, there is the propeller phase, which I have included, but I really reduced the efficiency because it's not really clear how this process works. Or the X-ray radiated accretion disk, which is also an approximation that I'm using. Okay, so firstly, we can look at the case of no pulsar wind radiation. And clearly you can see, also the color bar shows the surface hydrogen of the companion to the neutron star. And clearly we can see that, okay, there needs to be something extra going on there if we want to describe these black widows and redbacks. Although I will say that these very compact black widows, at the very least, they seem to be able to be reproduced without the need of any pulsar wind irradiation, although you will see that regardless of irradiation, these systems are always reproduced. Also, they seem to match well with the surface hydrogen depletion that is simulated. And in these two, maybe, I don't know if it's super clear, but there are two black triangles, which stands for that there are no hydrogen lines seen in these sources. There are two black triangles and one black cross. I will make this better next time. But, so most likely the third one also has no surface hydrogen, which is cool. Okay, and another thing that I want to point out is that a small part of the redback parameter space is also reproduced, very small part, but still is, and it seems to be connected to these compact black widows, and they pass through the ultra-compact X-ray binary regime. And this is because these systems, they start their Rostov overflow near the bifurcation period, so it's just before. And that seems to be a common, let's say, problem with the ultra-compact X-ray binaries, where if you use the standard magnetic braking prescription, which is this one, then to create these UCXPs, and also it seems like the redbacks and some black widows, you need to have a very narrow range of initial orbital period. And so there is some work that has been done to investigate this, that maybe we need stronger magnetic braking or something else that's going on. But in any case, since all black widows and almost half of redbacks show signs of irradiation, we should also look at the irradiation grids. So going from top to bottom, it's in increasing order of the F pulsar. And you can see that if you go to, let's say, 0.1, so increasingly with increasing F pulsar, you have more and more of the black widows that can be reproduced. Although for redbacks, it seems a bit more difficult and you need a lot higher irradiation effects. Also, I still have to check what's going on with these ones that are just going straight from one end to the other. But in any case, the main systems that seem to be affected and are at least crossing this region are those near bifurcation period binaries again. So think I was, okay. So basically, my conclusions are connected to my future work. So because of this connection to UCXP type systems that have this dependency on magnetic braking, it would be, hopefully, I will study different magnetic braking prescriptions to see if maybe that helps in creating more, or in getting a wider parameter space for red packs, or even a population synthesis study, because there can be so many things that are governing what is the initial binary that you get that undergoes this mass transfer phase, and hopefully a combination of these two will help. Okay, thank you.
Plenty of time, thank you. So do we have questions?
No, they have double.
They have double choice.
Yes.
Okay.
Any other question?
No, so the spin evolution part is added in Mesa, so at each step
so
it
you
calculates.
implemented it?
Yes.
Oh, very, very nice.
Let's see how it works.
And this is available?
Not yet,
Okay.
hopefully soon.
Okay, very nice.
Is there any other question?
Yes, so I have this is, to be fair, like the equations that I've used are commonly used to do, yes, so basically from these three papers, so they have done a similar thing but using rapid population synthesis.
Yes.
And the, yes, to answer your question first, so I am calculating the magnetospheric radius
Yes.
using a simple equation, not nothing too complicated, but also I'm calculating the surface magnetic field as it decays with mass accretion. The thing is that the equation that I'm using, it has been constructed to reproduce like 10 to the 8 Gauss very quickly.
Yes.
So maybe there is some uncertainty there. It's not really like it's just directly proportional to the mass accreted, and that's it. Then
Right.
it stays at,
Okay.
yeah.
Thank you. Thank you.
Okay, let's thank our speaker.